All right, guys. Well, we're going to get started on today's program. Welcome to Flex Train, a flexible training opportunity brought to you by Johnstone Supply. So today I want to talk about the design and the history of thermostats. Sometimes as technicians, we kind of take it for granted where thermostats came from. We all started at some point, and it'd be safe to say at least most of us started with the T87. Even till today, this is my favorite thermostat. It was the longest production running thermostat ever made, and it was a diehard for a residential thermostat. So when we started talking about thermostats, I have a lot of guys, especially our counter guys and our call center guys, that just wanted to know about thermostats because they hear so much about communicating thermostats, and they wanted to know what was going on inside of that thermostat. So I thought we would step back a little bit and talk about thermostats and their progression through history. So, I like taking polls. Let's take a quick poll here. So what was a thermostat actually designed to be? A device that calculates your home comfort needs, a device that manipulates your HVAC demand system, a switch or computer that sends commands to your HVAC equipment. Because depending on what generation of technicians you talk to, I've actually been getting different responses on this. So 43% of the people have voted, and 50% have actually voted now. So we're getting a nice little mix. So I'm getting 70 some percent are saying that it's a switch, 20 some are saying that it is a device to manipulate the HVAC system, because that's actually what we're doing with a lot of our electronic thermostats today. And so when we look at what a thermostat was actually designed to be, it was designed to be a switch. That's all it was ever designed to be. So if we look at the history of thermostats, where they came from, what they were originally intended for, and how we have continued to use those in our industry, we find that a thermostat really has always been used to control temperature in some form or another. So Andrew Earle was a Scottish chemist. So a lot of the mechanics of HVAC started with chemistry and alchemism, because they were the people that were working with, at that time, what they considered alternative metals, things besides iron. They were working with bronzes and brasses and seeing how they changed, and they needed differently with different temperatures. So he was working with different metallic surfaces, and he developed what we would consider as a thermostat back in 1830. So he created a bimetal switch that he used to regulate temperature on machines for some cotton mills. And he also had a device that used a bimetal loop that actually controlled the temperature on a device that they used for fermenting alcohol. So they controlled the flame that was actually on the burner of the assembly. And it was a relatively simple device, but when we look at what it actually is, it kind of looks pretty similar to what we know as a bimetal thermostat of today. So this is the original patent, the first actually applied for patent from W.S. Johnson, that we now know as Johnson Controls. So it was a spring style thermostat that was actually used to do automations of its own. It was really a device that was used to control dampers at that time for a wood boiler. So in 1885, Albert Butz, he patented a device called a damper flapper, and it was a bimetal device that had a series of pulleys and rope connected to a bimetal temperature modulating switch that controlled the door, the damper door, that was on the furnace. So they actually controlled the amount of oxygen going inside of that furnace, whether it was being fueled by coal or by wood. It was just modulating the air coming into it. So he was controlling the oxygen that was getting into the combustion process. And it was very effective, because before then, you had a door and you would set a damper for, a certain amount of airflow, and that was the only amount of airflow that could get through there. So your heat load was actually dictated by the demand of fuel that was inside of your furnace. Well, this new invention actually allowed you to stoke your furnace very heavily and be able to control the amount of oxygen coming into that to regulate the temperature. And that design continued into that manufacturing process and to that industry, and it later became the Honeywell industry. So in 1927, Albert Butz's damper flapper company had actually merged into a new conglomerate, and it became what we know today as Honeywell. So Honeywell's original thermostat was actually a damper flapper control for the door of a furnace. And so our original programmable thermostat actually came in 1907. So in 1907, they just started looking at, hey, we can actually control things based not only temperature now, but we can start looking at things that are based on time. So they literally took a mechanical clock that had a tab that would actually flip that tab to break this switch so that they can actually set a time. It was typically only a 1 or 2 time per day switch, but now they had the ability to actually turn that thermostat on and off. So when we talk about programmable thermostats today, we think programmable thermostat came around, within the last 20 or 30 years. Not at all. The very first programmable thermostat was actually developed and patented in 1907 and was extremely popular for about 20 years. The only thing that actually slowed down its production was the fact that it was made out of solid brass. So by the time we got into World War I, the demand for heavy metals became, an extreme demand for military production. So the construction of the thermostat faded away a little bit, but our original programmable thermostat was built and used in 1907. So, which was created first? If we think about the design of them, most of us as technicians have seen both styles of thermostats over the years. We've seen bimetals, we've seen mercury. So, which one would you think came first out of the two? It's kind of what I was anticipating on seeing. It's almost split right down the middle. 75% of the people online have voted, 50% say bimetal, and 50% say mercury. And in fact, it actually was mercury that was our first thermostat. And I was even surprised of how far back it went. So back in the 1600s, there was a Dutch engineer and inventor that built the first navigable submarine. So it was actually a steel and bronze submarine, and he created a variety of different mechanical mechanisms. And one of them was a device that used mercury to control temperature inside of a baking oven. So it used mercury, it used alcohol, and it allowed the mercury to set on top of the alcohol, and it became a float that modulated the amount of air that was coming into the system. So it did a modulation of the temperature based on the flow of air that was allowed through the air tube coming into the combustion chamber. So we've been using mercury to control temperatures all the way back till 1620. So as we progressed, we use different types. We use bimetals, we use mercury, we went into electronic solid state style. So if we're talking about a bimetal thermostat, a lot of this younger generation have not seen bimetals because we've not been using them for a long time, but they were extremely popular. The bimetal was just simply a switch. I'm going to grab my pen here real quick. A bimetal switch simply used, if we look at the switch itself, had R coming in, so we had a supply of 24 volts coming in to the contact point, and it had a magnet that was actually on our spring coil. So our spring coil was two dissimilar metals that were bonded together so that they would stretch at different rates, so that as temperature changed, the metal spring would flex because of the change of the dissimilar metals, and it would cause that magnet to shift. So as that magnet would get closer to which side of its switch, it would actually just pull that arm over and make contact, and so it could swing either direction based on the strength of that magnet. Very common thermostat. They were fairly reliable. The downfall of them is they just weren't extremely accurate in their tolerance. They were adjustable. We had the ability to set heat anticipation on them. Greg, are you on this morning? No, Greg must not be out here. Greg's an old school service manager that works for us out of Dayton, and he likes to talk about setting anticipation. I think he covered that last week when he was talking about transformers a little bit. So, it was a thermostat. It had control of heating and cooling based on the tension that was on that bimetal spring. And it's pretty effective and fairly inexpensive to manufacture. So we use bimetal thermostats quite often. Mercury has typically been the most accurate style of switch. As long as it was contained within a sealed glass chamber, mercury didn't pose any type of a health threat. Today we look at mercury as being a dangerous substance, but we've been using mercury since the 1600s for thermostatic controls. At Johnstone Supply, we keep a recycled bin for all mercury thermostats that come back to the facility, and we send them off to be recycled because it is a caustic substance when absorbed into the skin. But man, it makes for a good switch. So we've used those in most of our thermostats for the last 50 or 60 years. With that mercury is a conductive liquid, so it flows very easily, so it doesn't take much movement of that glass vial out of horizontal to be able to use it as a switch. And that's all that we're doing with our mercury. We're just allowing it to flow electrons whichever direction we need it to go. If we look at a multi-staging thermostat, now all we're doing is we're just putting in multiple vials of mercury that are slightly off on their horizontal pitch so that we can get a degree or two of change between those so that we can stage in single stage and two stage of our gas or of our heat and single stage and two stage of our cooling. So with this particular Honeywell thermostat, most of you guys out in the field have probably seen this if you worked on commercial applications. We were just simply using two sets of switch for either side, two for heating, two for cooling, each of those with a 1 or 2 degree differential between the two of them. And all that means by making a differential is that we adjusted its horizontal just a little bit. So if we look at, let's look at the ones over here on the right. If we look at these two, we can see that our one that is closest to temperature is going to be relatively horizontal, and our one that's going to be pitched off a couple of degrees has got just a little bit of incline to it. So it's at a slightly different angle than what the other mercury bulb is, just so that we can get a little differential between it. So we can stage now our thermostat based on the angle of levelness in our mercury. So if we look at that and what's going on inside of that thermostat, this is the actual wiring diagram that came with these thermostats. Most of these were used in the 70s, 80s, and into the 90s. Most of them have disappeared by the 2000s as we got into solid states and got into chronotherms and the like of such. But if we look at what they were doing inside of that thermostat, it simply is a switch. If we look at our loads here, I've got to move one of my screens in front of me. W1, first stage heat, is going to be contacted on this switch. So as that mercury bulb falls, we're going to drop. As the mercury bulb rises, it's going to make contact for our switch. There's our contact points right there. Stage 2 for that is going to use this secondary mercury bulb, and that is going to be contacts for stage 2. If we're on the cooling side, so we've moved our switches inside of the thermostat and we're now into a cooling position, we're going to use stage 1 right here, and we're going to use stage 2 right here. So it's just switches. We've always had switches in our thermostats. So as we progressed, we had to look at how we're going to manipulate our switches over time. So we started getting into digital thermostats. And we started getting into different types of thermostats, and particularly as our equipment is progressing into time now, we're getting into modulating control. So we're getting into equipment that's going to need modulation of its signal. It's going to need its switches to now not only be just an open closed switch, it's going to need to be something that's going to be able to have variable control, because we're going to start using variable voltages to do that. So as we moved into communicating equipment, we started altering our thermostats pretty drastically. We started using those thermostats because as technology was increasing, our thermostats was moving right along with it. Everything, once we got into the digital technology, the age of technology, everything started developing. The sad part about that is our thermostats started escalating in their manufacturing costs because of all of the controls that were inside of those things. And so manufacturers started building these very elaborate thermostats to operate their very elaborate control networks that's inside of their HVAC systems. And our thermostats started getting very, very expensive. We've had some different generations of them, but when we're talking about communicating thermostats, we're now talking about thermostats that are not using switches. We're talking about thermostats that are using variable voltages, and every manufacturer has their own type of communicating thermostat that is a variable voltage thermostat. If we look at the progression of Daikin, Daikin had been using the CTK04 thermostat, which is on the left, and they are now moving into their own proprietary thermostat, the Daikin 1 Plus thermostat. And when they were talking about fully communicating in the one on the left, it didn't have contact switches. It had to use auxiliary contacts either in the furnace or in a electronic interface module to be able to make switches, because we still have appliances that need to be switched. Even if our outdoor unit has an inverter compressor and it is modulating, typically between 35 and 100%, or if we have a variable speed blower that's modulating the same way, or if we have a modulating gas valve, we're not using just a switch anymore. We're actually looking for different demand levels. So we use a 5-volt DC signal to do that, but we still have things like humidifiers that we need to run. We still have UV lights to turn on. We still have things that operate on switches. So the thermostats were just really starting to get complex in how they operate and how they manipulate that HVAC system. But when we talk about the new Daikin 1 Plus, we're actually talking about a thermostat that is doing both now. So it is a communicating thermostat, so it's operating its equipment, the indoor unit and the outdoor unit, with that modulating 5-volt DC signal, and it also has switches internal. It has internal contacts, so it's using relays to be able to turn on two devices. It has two sets of contacts in its faceplate. If we look at what has happened with Carrier over the years in their modulating equipment, they went the same direction as far as putting all of the modulating capabilities inside of that thermostat. So when we get talking about the Carrier, like the Infinity systems, we're talking about systems that are removing the switches and now doing modulating at the thermostat. It's expensive technology. If we look at any manufacturer's communicating thermostat, to the homeowner, it's going to range between $600 and sometimes $1,000 to the homeowner for this thermostat, because it is a computer. It's actually computing and using algorithms to control the demand that is happening on that equipment. So the days of switches disappeared when we got into communicating technology, and it is continuing to evolve in some manufacturers, and the thermostats are getting more and more expensive. Because I get this question all the time from guys, especially at the counter, like, man, why is that thermostat so expensive? Isn't it just a thermostat with a nice pretty screen to it? And it's like, well, no, not actually. Most of these are operating on 24 volts only to power the screen and the electronics and the Wi-Fi modulator for it. Some of them do still make switches. We're going to talk about those here in just a second as well. But the most advanced thermostats now that we have on the market don't have switches in them anymore. They are a true variable modulating voltage that controls the operating demand of the system. If we look at the Climate Talk system, so the Linux iComfort system, same thing. Exact same operating platform. It's just their own proprietary. So they've had a couple different changes in their thermostats over the last decade maybe, but they're all using the same technology that Carrier was using, the same technology that Daikin was using. They're using a variable DC voltage coming out of this thermostat to control the modulation of the furnace and the modulation of the outdoor unit. These are typically a 3 or 4 wire installation, but it is simply 2 separate voltages. A 24 volt AC voltage to power the electronics and a variable DC voltage to go back to the equipment to tell it what it is doing. The downfall of all of these different communicating platforms is that they built their own proprietary software for them. You can't take a Climate Talk thermostat and put it on a Carrier Infinity system. Even though they're operating at the same voltage with the exact same principle, they talk within different algorithms and they talk within different bandwidths, so they don't actually communicate to each other, even though they're talking on the exact same principle, the exact same philosophy. If we look at the Train, the Comfort Link system, exact same thing. They've had some changes of the actual design over time, but it's still the same principle of communicating technology. The switches have been taken away, and it's a variable controlled signal. The one that has changed everything, and it's the reason I spend so much time with the Comfort Bridge platform. We do a lot of Comfort Bridge platform training. I just did one yesterday over at Indy East for a new Amana dealer. Does everybody understand that merger between Amana and Goodman? Goodman bought Amana for that mandrel bent tubular stainless steel heat exchanger technology. Which Goodman doesn't get the stainless steel version of it. They get a aluminized steel version of that. And when Daikin came to the United States, Daikin already had their plan to become the largest manufacturer and distributor of HVAC equipment in the United States. They just came to the United States and seen Goodman sitting there with the largest distribution network in the United States already developed and went, you know what, we think we'll go ahead and buy you so that we don't have to worry about our infrastructure. And hey, that's great. You've already got an awesome heat exchanger. We love that too. They came in and built 3 completely different product lines. Daikin is still staying on that communicating platform using that variable DC voltage to control and to manipulate its equipment. Amana is running in its own direction with an entirely new principle that was just mind-boggling. It was a big reason that I came back to the residential HVAC field to be able to do training and to be able to do education on this stuff, because it is an absolute game changer. And it is, in my opinion, it's how we should have stayed with our technology. Goodman is now in the background going, hey, big brother, can I tag along with you? And so Goodman is actually reaping some of the benefits of Amana just by that partnership that they have. So even the Goodman furnaces and outdoor units of today within the last few years are nothing like they have been in the past. Especially if we're talking about communicating technology. If we're talking about an entry line 80% multifamily furnace, it's still an 80% multifamily furnace. It's always going to be that way. There's a market for that. But in that communicating world, that's where things changed. So Amana came to the platform and went, you know what? A thermostat has always really just been a switch. It's all it was ever designed to be. And somehow we got away from that and we turned it into a computer that doesn't talk to any other computer. It only talks to its own network of computers. And that's like the silliest idea ever. Why did we do that? And so they went and they redesigned their entire communicating product line. It's going to be the entire product line. And they simply said, why don't we put all of that modulating algorithms back into the equipment, and we'll just let the thermostat be a switch again? Because they started seeing this change in our industry. 10 years ago, the HVAC contractor was the person that installed the thermostat, right? We knew what worked best with our equipment. So we supplied the thermostat. Most of the time, the homeowner didn't even have an option of what thermostat they were getting. They got what we preferred. That all changed when third-party manufacturers got involved in our industry. When Nest and Ecobee entered the field and they started building thermostats that were more focused on home automations and the ability to communicate with other IoT networks, Internet of Things networks, that's what changed our industry. Because now we had people that were building their HVAC systems based around their thermostat. And these thermostats are switches. That's it. They have the exact same principles of every thermostat that we've ever manufactured in the past. They use a switch or a relay or electronic contact to be a current contact to be able to control our flow. Amana took advantage of that opportunity and said, hey, you know what? This is a great opportunity for us to build all of our own algorithms. And oh, by the way, we got these really cool engineers from Japan that have, now bought us. I'm sure they'll sit down and help design some pretty interesting technology. And so they completely rebuilt their entire product lineup. They took all of the modulating algorithms that would have been in the thermostat and they put it back in the equipment. So now all the equipment needs is a switch for am I hot or a switch for am I cold? And then it uses its own algorithms to control lets the equipment use its own algorithms to modulate how much of a demand on the equipment that it actually needs. And it was a game changer. And a lot of people don't know what's going on with that right now. And I'm here to tell you, this is the way that we should have handled modulating equipment going forward, because our thermostats for communicating equipment keep getting more and more expensive. Well, now we have communicating equipment that doesn't care about a communicating thermostat. It just wants a switch, and it's going to modulate its equipment based on the amount of time that switch is being closed or being open. And I asked myself, why didn't we do that? Why did we let technology take our thermostats into another direction? And there are people that will argue and call, oh, well, yes, we have more modulating control, we have faster reaction time at the thermostat, and that's probably true. But when it comes down to it, would you rather have a $1,000 thermostat that probably will not control your home automation systems, or do you want a $250, $300 thermostat that will do the exact same thing? Better yet, why don't you keep that T87? It's just a switch. That's a switch for cooling, switch for heating, and that's all this Amana modulating equipment needs. I can't tell I'm a fan of this modulating equipment. All right, so let's finish talking about these communicating thermostats. ICP, observer, same thing. It's communicating. It's using a variable 5-volt DC signal to talk back to the equipment. So one of the questions that I had from my counter guys when they were talking about communicating equipment, they had a customer call them that had a Linux communicating thermostat, and they wanted to know if they could get a replacement communicating thermostat to operate their system. And they knew that the Prestige IAQ was communicating stuff. And I said, hey, can we just use that? I was like, whoa, 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 different communicating. So I'm gonna move some light real quick. I'll be right back. So if we talk about that style communicating equipment, it's a little different. It is communicating, but it's not communicating variable voltage back to the equipment. It's communicating the switches. So we're talking now, we're just using radio frequency from the thermostat. So the thermostat itself, grab my Sharpie, and these are our two different generations that we have seen of our IAQ communicating thermostats. And I know everybody out there has got some type of the same system. I like the Honeywell. So it just simply is using 24 volts to feed the thermostat. The thermostat is going to radio communicate back to the electronic interface module where the switches are stored. So it's literally a wireless thermostat of switches. It just has this nice big old screen. By the way, I have the one on the right at my house because I have an older HVAC system that operates on switches, but I love the thermostat. So it's a really, really good concept. It is a communicating thermostat. The thermostat communicates by radio frequency back to the electronic interface module, and the interface module does the switching. So it is not the same platform of communication. We have a variety of platforms of communication going on now, and this one just uses radio frequency, and we'll talk about those frequencies here in just a second. So if we look at the inside of an electronic interface module, and like I said, this is just a Honeywell. There's other brands out there that use the exact same principle. They use a communicating thermostat, which all it is radio frequency from the thermostat back to the interface module, and the interface module is going to do the switches. So if you look inside of there, you know, we're making all of our contacts for whatever devices we're operating, but when it comes down to it, I am switches. That's all I am. I'm just relays that's making switches for W, for Y, for W1, Y2. That's all it's doing. And you can see those on the right-hand side a little bit closer, what's going on inside of there. So most of that board is for communicating. The rest of it is just for doing the switches. Great thermostat, by the way. So here's what's going on with those frequencies when we talk about how we're communicating on these things. If I'm talking about that Honeywell red link, that IEQ or any other red link that we're talking about, they're actually talking on the 900 megahertz frequency. Everybody remember cordless phones for home? 900 megahertz? That's all that we're doing with RedLink. We're literally just using radio frequency, and it bounces between 902 megahertz and 926 megahertz. It tries to stay away from the Z wave, which here in the United States is 908.4. If you go to Europe, it's actually 868. So it tries to avoid the Z wave because there are a lot of appliances, other appliances that's talking in that 908 range. So it bounces back and forth. So if you're using a frequency monitor to look at the radio waves that's being produced by a Honeywell RedLink, you're going to see that it's going to bounce between 902 and 926 megahertz. It's just a radio frequency. That's all that it is. If we talk about Wi-Fi, depending on which network you're using, you know, you got 2.5 gigahertz, you got 5 gigahertz. And what people don't realize is when we're talking about the frequency that something communicates on, the higher the frequency, the more information that we can cram in there, but the shorter the distance that we can actually transfer efficiently. So like we talk about whales, you know, whales can communicate on very, very long distances because they use extremely low frequencies. Most of the time they're below the audible reference of human beings. So the lower the frequency, the further we can allow that sine wave to travel. The higher the frequency, the shorter it's going to travel. So yes, a 500 gigahertz signal can hold more information, but it can't travel very far. A lot of times it won't even get to the edges of the house. We can use 900 megahertz, lower frequency, and actually communicate further distances. That's the reason we can use outdoor temperature sensors, Wi-Fi or wireless outdoor temperature sensors, not Wi-Fi, I'm sorry, wireless outdoor temperature sensors, and we can put them anywhere we went to outside, and they're going to actually communicate. Wi-Fi, not necessarily the same opportunity because of the distances. We have Nest now using what's called a weave network. So if you have a Nest or any Google product, it actually uses both bandwidths, and it bounces between 2.5 and 5 to find the greatest network. So you could have a Nest thermostat, and when it's connected to your Wi-Fi, it's now actually a home Wi-Fi extender because it's weaving through all of your other devices. Z-Wave, so we've talked about that. That's been used a lot in today's communicating or wireless products. It's operating at 908. And then regular Bluetooth, if we're talking about Bluetooth devices, like this new Amana Comfort Bridge technology that I was talking about, they have now incorporated a Bluetooth communicating module in the furnace and in the air handler so that I can talk to that piece of equipment using my phone. Bluetooth operates at about 2.45 gigahertz. So on those Amana modulating or those Amana communicating furnaces, they now have about a 50-foot distance that you can connect to that furnace and actually communicate to that furnace. It's a pretty decent platform to be able to utilize. But Honeywell is still going to continue using that red link, that 902 to 928 megahertz frequency, because they can travel for a long distance. So if you have an application where you are having a multi-stage, say you got a two-stage heat pump and a two-stage gas furnace, and you're working on an old home that has, you know, an antiquated control wire. It's only got 3 wires running up to the thermostat, and they've been stapled to the studs and they've been finished, and you can't do anything about it, but you need to be able to stage that system. Well, now we can just simply run 2 of those wires to feed power to that Honeywell Red Link, and that Honeywell Red Link thermostat is going to send a 902 to 926 megahertz signal back to that interface module. And we can control all of our switches, however many we need, at that electronic interface module. So it's communicating, but it's communicating in an entirely different way. And as we move forward with thermostat technology, this is what we're seeing, and this is what you guys are going to see in the field. The reason we need to go back to switches is because now our thermostats are not just a thermostat. Our thermostat is part of a communicating network between all of our other devices in our home. It becomes a part of our home network. That's a game changer. But that's where we are. Our thermostats are now part of a network in itself, typically operating in Wi-Fi, but can also be working in some of the other frequencies. But typically it's going to be operating in that 2.5 to 5 gigahertz Wi-Fi range. So we had to have third-party manufacturers getting involved with our thermostats. It's basic supply and demand. Our generation of consumers are building their home automation networks, typically based around Alexa and Google Assistant, and they're buying thermostats that they love. So if we go into a home and that consumer is wanting a communicating, modulating HVAC system, and they already have their Ecobee that they love and their kids love talking to it, do you want to be that person that goes in and says, you know, I know you love your thermostat, but it won't talk to our communicating equipment, so we have to take off your $250 thermostat that your local electric company just give you, because we have now electric co-ops and electric energy providers that are providing these thermostats at no charge. At least here in Indianapolis, you can get a Nest for free. For free. So you're gonna have to take that nice switch off the wall and put this $600 to $1,000 communicating thermostat that is proprietary to your equipment. No one wants to do that. You're going to need to be able to go into that house and go, yeah, I'll sell you whatever equipment you want. And yeah, I love that you have your Ecobee thermostat. I'm going to go, actually, we're going to set it up for single stage heat and single stage cool. So it's just 2 switches. And I'm going to use that to run your new 20+ SEER outdoor unit and your new 98+% indoor unit. And it's going to be a happy customer. So Amana's already done with their product line. How fast do you think everybody else is going to do that? So the days of expensive communicating thermostats are starting to go away. We put computers on our wall to be very elaborate, very expensive switches. When if we would have simply put those switches back in the equipment where they were supposed to be, we could have stayed away from all of that mess. So yeah, you're going to have systems that will have to have a communicating thermostat. It's hard to say what the next generation of HVAC is going to be. But right now, I can hit 23 SEER on my outdoor unit, and I can hit 98.2% on my indoor unit, and I can control it from a switch. Sounds like a pretty good option to me. So be aware of that thermostats are going to be moving back into being switches so that they can operate at a platform that talks to every other device that's in the home. And if you don't understand that, if you're not part of that, you're going to be left behind, because this is the world as HVAC technicians that we are moving into. And that's what this program is for. This program is to just stay ahead of things, talk about changes, talk about things that are going on. Because if you think about a new technology that comes to any industry, I don't care what it is, if somebody comes in and designs something that allows for same performance at less cost, everyone's going to jump aboard. So it's literally a matter of time before every other manufacturer starts moving away from these expensive communicating thermostats, starts putting the technology back into the equipment itself, and allows a thermostat to be a switch. All right. So here's briefly what some of this Cool Cloud stuff looks like. Like that Cool Cloud, that Comfort Bridge technology, I can operate that furnace and that air handler from my phone. I can operate it from the furnace too. By the way, they got rid of all the dip switches, so it's now just like 3 buttons: left, right, enter. And everything that I want to do from this furnace, I can do from my phone, because I'm now just talking Bluetooth from my phone directly to the piece of equipment. I can do any setup that I want of that equipment. Even on an inverter, I can look at my suction and transducer. I can look at my temperature sensors, all right here. That's where that sensor data screen is over there. We can look at the control operations of it. We can look at the status running condition of it from our phone. So we built these expensive thermostats to be able to do all of that. That's the reason that we built them, is so that we can look into the system, look into the network. Well, now we have the ability to do that from our phone. If I'm hooked up to Wi-Fi, I can do it from anywhere, like we are right now. We are just simply connected through a network. This is just software that I use. I put my input in it, you guys put your input in it, it goes into a server, and it comes back and we all get to see it. Same thing. So that's where our industry is going. And it's a game changer to some people who have been used to selling and installing communicating equipment. When guys change brand and come to me and install a Mana, and remember the top end Goodman communicating equipment has gotten this technology as well, they immediately go, why didn't everybody do that? And I go, I know. Why didn't we just leave a thermostat to be a switch like it's supposed to? And so now we're back to doing switches. Anybody got questions? Well, guys, that's all I've got for today on switches. So I thank everyone for joining us again on Flex Train, and please check us out on the YouTube channel. Like, share, make us known. Our community is starting to grow, and I enjoy having you guys with us every week. So, Greg, thanks for joining us. Everybody have a wonderful, safe day. It looks like it's going to be beautiful, and we will see you next week.